Hello everyone, welcome back to Calculus 3. Today I'm going to go over section 14.6 in our textbook. It is about directional derivative and gradient vector. Okay, so first let's recall what we learned before about partial derivative. Say you have a function of two variables, or maybe three variables. Say fxy, right? And we talk about fx or df over dx, just different notation about the same thing. Means what? You take partial derivative of that function with respect to the x value, or fy, which is df over dy, and that means what? You take derivative, partial derivative with respect to the y value. And what does that mean geometrically? Only work for 2 or 3 dimensions, because if you have a 4 or 5, and it's very hard to demonstrate with geometry. Okay, so say you have a surface. Okay, this is the surface. Imagine that, right? And you have a point. So this is the y, is the axis, y-axis. Okay, you take the derivative with respect to the x, means what? This is my x-axis. Okay, it's tell you what the rate of changes of the function f, or the rate of change in z on the x direction. So how high or how low is that point going to change? A little bit higher, a little bit lower on the x direction. And similarly, fy means what? The rate of changes of z on the y direction. And this is what it means by partial derivative with respect to x, or partial derivative with respect to y. See, you have a surface, right? This is a point, right? The point has a z value, right? So if you move along the direction to the x axis, how is that z value going to change? It's going to be a little bit higher, a little bit lower, okay? Or if you go along the y direction, this is the y direction, how is the value of the z going to change? So it's called what? Derivative with respect to x, derivative with respect to y, the rate of change of z in terms of x, or the rate of change of z in terms of y. So today in this section 14.6, we'll be talking about the rate of change of the z value, or z is a function, all right? The rate of change of the function f, or the rate of change of z, in any direction, not just x or y. Maybe you have direction right here random. Say the with vector u. That's direction u. Okay. Now that's what they try to tell you about directional derivative. Derivative on a direction. Okay, a random direction. So let me keep that f. So another way, we're gonna find the rate of change of z in that direction u that you are given. Okay. The first condition that you need is you need to be a unit vector. And what do we mean by a unit vector? It's a vector that got the length equal to 1. Okay? And the notation, you guys can look at the definition in the book. You use a limit, but let me just through you right away. This is a theorem that gives you the formula to calculate the derivative of the function f on the direction u. And you know this way: d vector u, subscript right here, and then function f. Okay, and I think that with x comma y, and to be honest, we're lazy, so most of the time if you understand the variable, we try to skip x comma y to make a shorter writing of this notation. Okay, and this is a formula for it. The directional derivative with respect to the direction u, and keep in mind that you have to change u to the unit vector. Okay, you have to have u as a unit vector, say in 2 dimensions, right? So u is say a comma b. This is a unit vector. And what do we mean by unit vector? Square root of a squared plus b squared is going to be equal to 1. Okay, magnitude. And if you have a 3D unit vector, it's going to be ABC, then what? Square root of a squared plus b squared plus c squared equals 1. Okay, and the unit direction derivative is going to calculate this way: fx times a plus fy times b. And again, I'm being lazy in here. Fx means partial derivative of the function f with respect to x, and fy here means partial derivative of function f with respect to y. And a here is the x component of vector u, and b here is the y component of vector u. And keep in mind that vector u gotta be a unit vector. Okay, and of course you can guess if you have directional derivative vector u in 3-dimensional space. So f of x comma y comma z, right? So if your new u is gonna be ABC, right? and you can guess the formula is going to be what? Fx, I should write x lower, Fx times A plus Fy times P, and then plus Fz times C if you have 3, and if you have 4 variables, and what? X, Y, Z, T or something, then you're going to be A, B, C, D, and you have X, F, Y, F, Z, and F, T, and then times A, times B, times C. Okay. So by similarity, if you have 2, then you do the same way for 3. And I need some room to write, so let me erase that part. Okay, and this is a theorem that helps you to calculate the directional derivative of a function f on the direction u. And what does it mean? This is what the rate of changes of the z variable or the variable of the function, the value of the function. I mean, the rate of change in the value of the function f on the direction of u is calculated this way. You calculate the partial derivative, and then you time the coordinates of the unit vector of direction unit vector, okay, and add them up. Or there's another way to think of it. Can I think of it this way? Fx comma Fy dot u or a, use mean a comma b. Do you guys remember the dot product? If I think of Fx Fy as a vector, right, and then ab is a vector, see? If you dot the two vectors, means what? X component times x component, y component times y component, and many people write this way. And this is what? This is the unit vector u, the directional vector. And this one right here, the vector of the partial derivative, is called the gradient vector. And you know that by the upside down triangle called the I think gradient f dot u. Okay. This one right here, we call it the gradient vector. How to spell gradient? Gradient vector. Of course, I give you two variables x, y, and by similarity, if you talk about gradient vector in 3 variables, you got what? Fx, Fy, and then Fz, 4 variable, x, y, z, ft, and so forth. Right? That's called the gradient vector. So in a nutshell, directional derivative can be calculated by what? Calculate the gradient, and then you dot product with the unit directional vector. You have the directional derivative. Okay? So really 2 things at once. The gradient vector is the vectors of all partial derivative of each component. Okay. Now we are talking about the dot product, and we are defining something called the gradient vector. So let me rewrite up here. Gradient vector is denoted by its notation upside down triangle f is what? Fx comma Fy. Of course, in here I'm using 2 variable function, but 3, 4, 5 you do the same way. Okay, and you have the unit vector u. Unit vector. I keep emphasizing unit. Okay? Unit vector u. Okay. So what we do in here is what we do a dot product. We take a vector, we dot another vector. By the way, this is notation of a vector. Okay. And recall the formula for a dot product before. You have what? A vector dot a vector is equal to what? The magnitude times the magnitude times cosine theta, where theta is the angle between the 2 vectors. And this for dot product. Okay, this is we learned a while ago. I think it's last chapter. Okay. So with this, you know what? Since u is a unit vector, so magnitude of u is always equal to 1. It's always equal to 1. So this is gradient of f times cosine of theta. And that gives you another idea. They ask the question, what would be the max when you have the max value for magnitude of gradient of f? This is whenever cosine equal to 0. Was that right? Because cosine is, this is a trig function. cosine trig function is always somewhere between -1 and 1. And you're going to have this one at max whenever this is maximum, and it's max whenever cosine is equal to 1. Right? In another word, if cosine is equal to 1 means what? The angle between the two vectors, the gradient vector and the unit vector is 0, means what? Those two vectors have the same direction. Then you have maximum gradient. Another way, what did you mean by maximum gradient means what? The rate of change of the function f is going to be maximum. F going to change the most whenever the gradient and the directions is directional vector is the same direction, and you have maximum. Okay, I think I should explain it a little bit more using geometry. We have function z equal to fxy, right? So you guys recall something called a level curve. Level curve. Say you have a function. Okay, this is functions z equal to fxy. Okay, and this is 3D. Okay, so you have some kind of curve. Can you imagine like a hill? So when you set a constant equal to z, so z equal to a constant, say z equal to 5, right here 5, you have a curve. This is a level curve. Okay. Interestingly enough, the gradient vector is always it's like a normal vector perpendicular to the tangent vectors of the level curve. So if I draw it this way, think of it. You look at from the top. Okay. So you have a curve, level curve like this. Okay. At the point right here, if this is your tangent line at the point, then the gradient vector is always perpendicular. Okay. And I'll try to connect it. This one means what? If, say, this is a level curve right here, you wanna, this is another level curve up here, and the rate of change of that gradient, the rate of change of derivative, directional, dUf. It's going to be the most if you keep walking this way, walk in the direction of delta f, this way. You're going to go up or you go down. This is the rate of change the most. You increase the z value the most, so you lower the z value the most. So, so if you move in the other direction, so you go this way, you go that way, then change a little. Okay. Hopefully that helps. Let me move on, see if, what else we have in here. We can talk about tangent plane to the level surface. Now let me talk about three-dimensional function, three-variable function. Say if I have a function f of x, comma y, comma z, of course, say w equal to f x y z, right? Then the gradient f is what? fx, comma fy, comma fz. So far, so good. See, I use the angle, angle parenthesis. I don't know what's called. It's called what indicate this is the vector. Okay, and last time I talked about what called a level curve. Now, if you set w here as a constant, you're going to have something called the level surface. And think of it as like a balloon. Say you have a ball, right? Ball. May not be circle. Something like this. This is for say w equal to 4, and then it increases. W equal to 5, you're going to have another surface. It's bigger, like a sphere, getting bigger, bigger. Oh, it's not just a curve anymore. It's like a 3-dimension because we have one more variable. Okay, so let me try some. Draw something that looks good. Have a curve. Okay. And the meaning of that gradient vector is what? It's actually the normal vector. This is the normal for the 3D function. Okay, it's going to be a normal vector. Really, you take partial derivative, 3 components, it's going to be the normal vector. And what is so good about normal vector? You guys can use this gradient to find the equation for the tangent line at the point on that surface function. Okay, so level surface right here. So you know the normal vector. If you know a point, then you know how to find the equation for the tangent plane, right? And recall what we have for the equation for the tangent plane. We have a normal vector. We have a point, normal vector, say A, B, C, and a point of, this is a point, x naught, y naught, z naught. Equation for the plane was what? A times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. It's going to be the equation for the tangent plane. So if you have functions, level surface function of 3 variable, I claim that the gradient vector is actually your normal vector, and that will be very helpful because A now is fx, B now is fy, and z now is fc, and if you have a point, then you can find the tangent plane. Okay? Isn't it cool? So this is pretty much everything about section 14.6. Let me give you an example. Okay? I'll give you an example then. See if I missed anything before I give you an example. Example. Just find an. I just made an equation, and w equal to x squared plus y squared plus 2z squared. I think this is an ellipsoid. Okay. Easy, huh? So I'll write this like f of x y z then. X y z. Then fx is equal to 2x. Fy is equal to 2y, and then Fz is equal to 4z. So the gradient vector is 2x, 2y, 4z. Okay. Say I have a point, given a point on the function. Say 1, comma 1, comma 2. I plug in x equal to 1, y equal to 1, z equal to 1. I have a value. Okay, f x1, 1. F of 1, 1, 1. Okay, and this is a point on the level surface. Can you find a tangent plane at the point 1, 1, 1? At the point 1, 1, 1? I make a mistake right here, guys. I'm sorry. F of 1, 1, 1 is equal to 1 squared plus 1 squared plus 2 times 1 squared. That's what I mean. 1 squared, which is equal to 4. So when I plug in 4 in for that point, can I find the tangent line? Sorry, tangent plane at the point 1, 1, 1 using the gradient vector. Yeah. X equal to 1, y equal to 1, and z equal to 1, my gradient vector will be 2, comma 2, comma 4. You see how I calculate that number? X is 1, y is 1, z is 1. I got the value 2, 2, 4. Okay? And I have the point, I have the normal vector. I can find a tangent plane. Tangent plane. At 1, 1, 1 is what? 2 times x minus 1 plus 2 times y minus 1 plus 4 times z minus 1 equal to 0, and I simplify, multiply them all out. See, the normal vector is 2, 2, 4, 2, 2, 4 for the normal, which is a gradient, and then the point is 1, 1, 1. Okay? I have a tangent plane. Okay. Let me see if I missed anything. Okay, this is done with 14.6, but I figured out in 14.5 I'm missing something that I forgot to mention, so let me add in here. So I don't have to make a new video. 14.5 continue. Just a little bit, but I should mention it to you. Say you have a function f, x comma y, where x is the variable, and y is a function of x, okay? Y is just a function of x. Say something like f of xy equal to 3x squared plus 2xy minus y squared, for example. This is the function where x is itself variable and y is equal to x squared plus 1, for example. So y is a function of x and x is a variable. Okay? So you want to calculate dy over dx, I think. Okay. See? And this is going to be this negative. I always got the negative reciprocal, just like the perpendicular line. The dy over dx is going to be negative of fx over fy. It's always like this. Okay? Of course, if you have y equal to x, you know this already, and then dy over dx you can calculate right away. The problem is you don't know this. All you know is what? Y is a function of f. And all you know is what? You have a function f. F right here. Fx over fy. Okay? So this is called implicit differentiation. You have a function of fxy, and it's two variables, x and y. Then you can take the derivative of y in terms of x. If you know that y is a function of x, it's always this way. Fx over fy, see y on top, x on the bottom. See, I usually call it negative reciprocal. Now what? X on top, y on the bottom. Okay. Example. This is my function, right? So fx is gonna be 6x plus 2y, right? And fy is what? 2x minus 2y. You see, it's 0 for y, right? This is 2x, right? So dx, or dy over dx, dy over dx, because I don't know what the function of y in terms of x is. All I know is what there is a function of y in terms of x. I don't know what it is. All I have is the implicit function right here. So dy over dx can be calculated as what? Negative fx over fy is going to be 6x plus 2y over 2x minus 2y. Okay? This is called implicit differentiation, as you guys learned before in the course. Right? Yeah. And similarly, what if you have three variable function? Say f of x comma y comma z, where z is a function of x comma y. Okay. Of course, if you know the function z in terms of x, y, and then you can calculate the z over dx, the z over dy partial derivative directly. But you don't know that. All you have is this. Example, f of x, y, z is equal to 2x squared y plus 3y x cubed plus x, y, z. For example, x, y, z squared. Just make it up. Okay? And then you want to calculate what? Partial derivative of z in terms of x, or partial derivative in terms of z in terms of y. In other words, dz over dx. Or you want to calculate dz over dy. And this is how I remember the formula. Negative reciprocal. So it's going to be what? Negative fx over fz. Of course, this one is what? Negative fy over fz. Okay? So if you have the implicit function right here, where x and y variable and z is the function in terms of xy, then you can calculate the partial derivative of of z in terms of x and partial derivative of z in terms of y. Apply the formula. What is fx? 4xy plus 3 times 3 is 9yx squared plus yz squared, right? And fy is 2x squared plus 3x cubed plus x z squared, and then fz, no z, no z, is going to be 2x yz, and you plug in here. dz over dx is going to be negative 4xy plus 9yx squared plus yz squared over fz, which is 2xyz with negative formula. Again, this is implicit partial derivative with z in respect to x, and I really don't know because the implicit function, because they have z in here, right? Derivative of z in respect to x. And similarly, you have derivative of z in respect to y. And this is the last part of 14.5. I forgot to mention until I move on to 14.6. So I apologize and add it in here. Hopefully that helps. Thank you very much for watching, guys. And this is the end of the section for this week. Have a good day. Bye-bye.